This video is on section 2.3, Statistical Graphs. So we're just going to look through some other ways that data can be represented. First, we're looking at qualitative data that's categorical. You can represent it in a pie chart, which is a graph in which the data is depicted as slices of a circle, where the size of each slice is proportional to the frequency count for the category. So here we see an example of a pie chart, and it had, I believe it was different ways or different reasonings for why a plane might go down during a flight. So pilot error, mechanical, sabotage, weather, other. Next, for quantitative data or numerical data, we have a few different ways we can represent it. We have a dot plot, a graph in which each piece of data is plotted as a point above its corresponding value on the horizontal axis. Dots representing equal values are stacked. So here we have the pulse rates of different people, and you can see this might represent 40 and 41, and then maybe 50 had two different data points for 50. The most common one was somewhere in the 60s, 70s, and it had several different data points that were the exact same pulse rate, and so that's why the stacks get so high. You can see when you have some repetitive data that you get those different distributions. So this kind of looks a little bit like a normal distribution, not quite. Next, we have a stem plot or a stem and leaf plot, which is a table in which each data value is separated into two parts: the stem, which is usually the leftmost digit, and the leaf, such as the rightmost digit. So if you had a two-digit number, your stems would be the left digit, so the tens place, and then the leaf would be the ones place or the right digit. So this 4 represents 40, and 0 and 2 would say that two numbers of the data set would be 40 and 42. Here we have 9, 0, 2, 4, 9, 6, 6. So the pulse rates that are represented there, so this is just another representation of this dot plot right here. The pulse rates represented in this part of the stem and leaf plot are 90, 92, 94, 96, 96. So 90, 92, 94, 96, 96. A frequency polygon is a graph in which line segments connect points whose heights correspond to the class frequencies. So we'll see in a future example, this is similar to a histogram, which we studied in the previous section, but instead of having bars that are right next to each other, it's almost like we put a dot at the top of each bar and then connect the dots. And again, we'll see that in a second. And last, we have paired data. And an example of this is a scatter plot. A scatter plot is a plot of paired X and Y coordinate data, where the horizontal axis represents the X data and the vertical axis represents the Y data. The pattern of the data is often helpful in finding a correlation between two variables. So a scatter plot is helpful when you can't really separate the X data from the Y data, where the two have to be viewed together to have context. So here's an example of a scatter plot. We have beach visitors based on the number of beach visitors and the average daily temperature. In relation to scatter plots, a linear correlation coefficient, using typically R, is a number between -1 and 1 that describes the strength of the linear relationship between two quantities. So if your R value is very close to -1 or very close to +1, you would say that your scatter plot is very, very linear. You could probably draw a line between the points. If your R value is very close to 0, then there's probably no correlation and the dots are all over the place. So this is pretty linear, and so we would expect these points to be closer to 1 than they are to 0, because those are, generally speaking, near a straight line. Or at least they have a linear correlation. All right, so what we're going to do is we're going to take some information and we're going to draw a pie chart. So it says, suppose a college has 440 freshmen, 320 sophomores, 520 juniors, 325 seniors, and 965 graduate students. Represent this data using a pie chart. So it's helpful if we're doing a pie chart to know what the total number is. So 440, 320, 520, 325, 965. So there are 2,570 students total. And then typically in the pie chart, you can just represent the categories like this and put the different names of the categories and leave it there. But a lot of times it's common to put the percentages, what percentage of that category represents the whole circle. And that helps us to draw out the slices of the circle anyway. So we'll go ahead and do that. So we'll figure out the freshmen, sophomore, junior, senior, and grads. We're going to figure out their percentages. So 440 divided by 2,570. This is 17.1%, about 17%. And then for us to draw it within a circle, you can use the 17%, or you can look at how many degrees of a circle it would be. And a full circle is 360 degrees. So 17.1% of 360 degrees is 61.6 degrees, or we'll say, oops, don't want that, 62 degrees. So 62 degrees, not percent, 62 degrees is what I'm going to be drawing for that slice. Okay, sophomores, 320 divided by the total, 12.45, 12.4, I'm going to say 12%. Which is about 45 degrees. Juniors, 520. 20.2%. (72, 73 degrees). Seniors, 12.6%, we'll say 13%. (45, 46), it's like kind of right in the middle. I'll say 46 degrees. Graduate students, 38%. (135 degrees). And I accidentally wrote percent on this one, but that should be degrees. Okay. You can graph these using the percentages or the degree measures. These little tick marks are actually every 7.5 degrees, which isn't very helpful, but 2 of them is 15 degrees, and that is kind of helpful. So I'm going to start off by drawing a radius. And you can draw it straight up if you want, or straight down, it doesn't matter. And you don't have to put these in any particular order. If you want to go in order, you can, but it's usually not the easiest. And I'm going to start with 135 because that's the biggest piece, and then I'm going to go and just do easy numbers from there. So 15, 30, 45, 60, 75, 90, 105, 120, 135. So that's grad students, 38%. Make sure you put the percentage and not the degree measure if you're using the degree measure to graph these. The next two I'm going to put together is the sophomore and the senior, because those two, 45 and 46 degrees, they almost add up to 90. And because this is messing with my eyes, I'm not going to just do a quarter of the circle because I can't really tell exactly which line is a quarter. I'm going to count. So 15, 30, there's 45, I'll make that extra long. 15, 30, 45. So we're going to go a smidge further than 45 because it's 45 and 46 degrees. Okay, so 45 degrees is 12%, and this is with the sophomores, and then 13%, and this is with the seniors. I'm just going to put SR. You can write more of the word if that doesn't help you. All right, and then I have 62 degrees and 73 degrees next. I think 62 degrees is slightly easier for me to draw. So I'm going to do 15, 30, 45, 60, and just a little bit more than 60. So 17% FR for freshmen, 20% JR for juniors. And there we've got our pie chart all divided up. You could also do that with percentages if you felt comfortable. The 12 and the 13, that's good for me because I could do 25% of the circle. 38 and 17%. It should be about half the circle. I don't know. It's whichever you're more comfortable with is truly fine. Okay, for the dot plot, we're going to use data from section 2.1 notes. So you might recognize this data. It has to do with ages. And we're going to take this data and we're going to represent it 3 different ways. So first with a dot plot, the numbers range from 21 to 61. So I'm just going to say 20, 25, 30, 35, 40, 45. And then you just put dots. So 20 is right here, so 21, 21, because there are two data points that are 21, so I'm going to put them on top of each other. 24, 25, 26, no 27, but there is a 28, 2 29s, 2 30s, no 31, but there is a 32, and a 33, and a 35, 36, 37, no 38, but there is a 39, there's a 40 and a 41, no 42, but there is a 43, there's a 44, no 45, no 46, but there is a 47, 48, 49, 50, no 51, no 52, but there is a 53, 54, no 55, 56, there's a 57, 58, 60, 61. So we can see here that with our data, the data values are pretty spread out, which is, that's a different representation, so we can see that. For the stem and leaf plot, we're going to put the stem as the tens of these numbers. So 20s, there are 30s, there are 40s, 50s, and 60s. So with 20, we have 21, 21, 24, 25, 26, 28, 29, and 29. And then with 30s, we have 30, 30, 32, 33, 35, 36, 37, 39. And I'm kind of lining them up so we can see how many numbers are in the 20s, how many are in the 30s. 40, 41, 43, 44, 47, 48, 49, 50, 53, 54, 57, 58, 60, 61. So this kind of shows us what we saw in our last set of notes, where we had that our values, our data values, were skewed right. We could see there's kind of a peak here. Most of our numbers tend to be here, and then there's a tail. As we look at the numbers in the 60s, those are not quite outliers, but less common. All right. For our frequency polygon, I decided to make your lives a little bit easier. I copy-pasted the histogram that we had from before. So this is the numbers representing our ages. On the side, we have the frequency. So you would not draw the histogram first. I just want to show you how the two pictures are related. You just go in here, and instead of drawing bars for a histogram, you would put a dot instead. So you'd put a dot at 3, a dot at 5, a dot at 4, a dot at 4, a dot at 4. And if you're unsure where I'm getting these numbers from, let me get out my notes. I'm just using this table, the classes and the frequencies that we had from this data from section 2.1, actually. So this is what the data looked like when we first worked with it. So I'm just taking the same data from before, and we're putting it in a different type of graph. So with a frequency polygon, you wouldn't have the bars there. Those were just to help us with our old data. You just connect the points with line segments. Okay, next we're going to look at some deceptive graphs. So the first type of deceptive graph is one that has a non-zero vertical axis. So here they were comparing oxycontin with a placebo to say which one gives more nausea, and they tried to make it look like the medication was, 10 times more nauseating than the placebo. But in reality, they just started this at 10%. And then went to 12%, and then from there went up by 2% each. Over here, if you actually spread it out equally along the vertical axis, you find that it was only causing nausea about twice as much. And so still having results where the medication was causing people to be nauseous, but not near as extreme as it appeared to be in the first situation. So that's one thing to be aware of. The second is in pictographs. Pictographs can make something look misleading because they're taking an object that's usually one-dimensional and relating it to a picture that has an area or has a volume or something. And that can be misleading because if you have length and width being doubled, your area actually quadruples in size instead of just doubling in size. If you have length, width, and height, and you're talking about a volume, and those measurements double, then the volume of the shape actually increases by a factor of 8. And so if you're talking about something doubling, then representing it with something else that has an area can be kind of misrepresentative. So here they talked about something that had to do with telephones. I don't remember the context of the problem from the textbook, but if you look at the numbers here from 151 million to 534 million, it's about 3.5 times more. So what they did here is they said, well, this side has a length and a width, so we'll make the width increase by 3.5 times, we'll make the length increase by 3.5 times, but because this is an area, it makes it look like it had some gigantic change, when in reality, the increase would look more like this, 3.5 times of increase. Here, if we actually look at it, because it's an area increase, you would have 1, 2, 3.5, 1, 2, 3.5. And how many of these little telephones would fit on this big telephone? Probably 9 of them or more, maybe 10 or 12 of them, if we take into account the halves. So that's something to watch out for, just because there's things that kind of fall apart when you're using geometric shapes to represent numbers like that. And that can be misleading as well.